it's useful to look at an example in this situation where we have here I've got a magnetic field represented by the blue X's, and let's assume it's constant. So our magnetic field is constant and it's pointing into the page, right, into the page, and it has some value. So it has some magnitude that I'm going to just write by the letter B. Okay, so B is constant, points into the page, and we have a wire. Okay, and the idea is that we have a rod that is in contact, a metal rod in contact with this wire. And let's set up so that the ends of the wire have very little resistance, and then the wire itself, that we have a resistor sort of set up, a load at the end. Okay, and so what we're going to do is imagine, or not even imagine, we'll just look at the situation where we pull this rod to the right, as we see, at a constant speed, so a constant speed. Okay, so I've got a couple of questions to ask that you might ask in a situation like this. But the first thing I want to do is to make the case that there is going to be an induced EMF and that there's going to be a voltage which is going to give us current through that resistor. And so as we look at this being pulled to the right, what happens is, you can think about it, we have one X right now, but as it goes further, we're going to have more X's. So in terms of our flux, which is integral of B dot dA, but in this case, B is constant everywhere, so it's B dot A. The area is into or out of the page as well, so that would just be B times A. Now the B is constant with time, but the effective area is changing because our area is getting bigger. And so we can actually describe this by a Y and say an X distance, right? So our area is X times Y, but then the X is getting bigger with time. So our induced EMF, the magnitude of it, is just going to be the derivative of this flux with respect to time, which is going to be derivative of B times A with respect to time. Our B is a constant because it's constant and into the page. It's not changing its direction. So we can pull that out, and then we're just going to have derivative of the area with respect to time, and then the area is just going to be X times Y. So this induced voltage, this induced EMF, is going to be the value of the magnetic field times the derivative of X times Y with respect to T. But Y is fixed. That's the height of this. X is actually changing, right? Because as we pull this to the right, we get a bigger value for our X. And so this becomes B times Y dx dt. Now dx dt should hopefully remind you of something. That should be equal to your speed, your constant speed. I'm going to try to use a lowercase v for velocity to keep it separate from a voltage here. So this constant speed v is the speed that we're pulling this with, okay? So we get an induced EMF that's equal to by times v. So if we have all the values, if we know b, we know the size of y, and the speed, then we can actually calculate this voltage, and then if we know the resistance, we can find the current. But let's find the direction of the current. So direction of induced current. It must be induced because there's no battery set up here, right? I've just got wires and a resistor, but I don't have a battery hooked up. But this moving is like hooking up a battery to this. So the direction of induced current, well, we want to set up, we want to oppose the change in flux. And so what we're seeing is we're getting more X's, if we like, right? We're getting a bigger number of X's in the area. So what we want to induce is we're going to oppose this change. So if we don't want more X's, then what we'll induce is some dots. right? Some into the pages. So for a magnetic field into the page, we can kind of do our cheat sheet here, or we can create this on our, that's my current. I kind of find it useful to have this on my equation sheet so I can just look at it, right? This gives me dots, I think, and that gives me X's on the inside. Double check with your right-hand rule that that's actually the case. So we want, because we want dots, we want a current that goes in that direction. So that means a current that looks like this. So that's the direction of the current through this setup. That's I. Okay. And so we can say this is our EMF, or our voltage, if you like. I'll use a capital V. Our voltage is V times Y times the speed that we're going. And so our current would just be our EMF over our resistance, or our voltage over our resistance, if we like, and that would be VY times V all over R. Okay, and we would have some numbers that we could put in. Okay, great. Let's see if this makes any sense. I've got current here, right? This is my current that's going around. It's the induced current that creates the induced magnetic field. And now we can ask, what is the direction of the force on this bar? Okay, so if we look at this bar, I'm going to redraw it down here. Right, so I'll get rid of this. So I've got a little space to work. I've got my bar, and I've got current that is this direction, and a magnetic field that is into the page, right? That's the direction of B, into the page. Into page. This is I. So the force on that, force is equal to IL across B, right? And L is in the direction of the current. So if we do our right-hand rule, this would be in the direction of I, so that would be index finger. This is going to be middle, magnetic field if you like, and thumb is force. So if I do that, if I take my right hand and take my index finger sort of up, right, and my B into the screen, my middle finger into the screen, then I'm going to have a force to the left. That would be my magnetic force. And notice this is a force that opposes the motion, right? So I have a force that acts like this, a magnetic force. And you can do the same thing for the top and the bottom and find that the top and bottom bars, the forces cancel out. And here, as long as this isn't moving, we don't have to worry. I mean, there are forces on it, but we're not going to worry about that, right? You can do all of these things. This will be a force like that. But the bar is the only thing we're pulling, right? So I and B, so we had a force. I cross B gives me a force this way. So the top and bottoms cancel out. The leftmost force is there, but it's not being moved. So we really just look at this setup. So in order to have this move at a constant speed, we have to apply a force. So the force applied must, let's spell that right. Force applied must be equal to the magnetic force, so that we can say the sum of the forces on this bar is equal to 0 to go at a constant speed, right? And so the force that's applied is just going to be I times this length, which would be Y, times the magnetic field. And this is not the induced, but this is the external magnetic field. So it's this same one that we had all the way up here, right? The same value, 2 millitesla, for example. So that's the force applied. Now, we can, if we remember even more of our intro physics, and this is reaching way back, we can remember that power is equal to its watts, which is joules per second, right? Power is joules per second. That's a watt. So that is a change in energy over time, or change in work over time, which could be force times displacement, delta T. If we have a constant force, as we would here, force, we would have delta T, delta D, change in displacement over time, or force times our speed. So the power that we put in by this applied force, the power provided by the applied force, is just going to be equal to the force applied times V, which is equal to I times Y times B times V. So that's the power that's provided. We can contrast that with the power that's dissipated. Okay? So the power that's dissipated in our resistor, power for a resistor, right, is I squared R, if you like. And so that would be B squared Y squared V over R squared times R. And so these R's, we get something that looks like this, and we're like, wait, does this quite work? But of course, I need to substitute in for my I, which I can use this expression. So I get BYV over R. That's for my I right there. YBV. And I think you'll see that we get exactly the same expression above. So the power that's provided by the applied force is equal to the power dissipated by the resistor. Okay, so that's a connection between everything that we've done, right? We've got Faraday's law here, and Lenz's law tells us about the direction. And then we go back to forces in magnetic fields right here. And then we go back to physics 1 right here to get to power and how it relates to energy. And we go back to circuits to find the power of a resistor. So this is sort of pulls all of these things in together. And it says that if we're pulling this with a constant speed, we do have an applied force, and that's equal to the magnetic force that's resisting this motion. And it's resisting this motion because we have an induced current. So that's more justification for why that's the direction of the current, because it's opposing the change. And so we actually have to apply a force to then get this to have more and more magnetic field inside this window here of the growing rectangle. And so this just puts all of it together. Certainly you could have some numbers, but this lets you know how this all works.